So we're going to finish up on the question that we had for last class, and then we're going to move into basically applying this to larger molecules. Trip, do you have a question about this?
So the iClicker read wouldn't let me log in. It won't load through.
Okay, someone else got kicked out of their iClicker and wouldn't let them log in. So maybe just try in a few minutes and see what happens. But in the meantime, just... Sweet, you just have to ask and then it works. Okay, so what I want you guys to click in is which of these is the most polar of these bonds. We have 44 clicks, that is almost every one. How do we determine which is the most polar of these bonds? Hear from lots of different people today. Savannah?
Is it the difference between the electronegativity, like the largest difference between the electronegativity is the one that's the most polar?
Absolutely. And so a lot of people say it's the one with the most electronegativity or the least electronegativity. It has nothing to do with the absolute number. It has to do with the difference between the two that are bonded. And so the way that you'll see this written out is delta, which is the difference, in electronegativity. So mathematical triangle means delta, which means difference. So if we're asking about the most polar bond, you're always going to look for what's the electronegativity values. Do you guys have to memorize that whole table?
No.
That would be a bad idea, right? Waste of brain power. So I will give you this on the exam because the one I gave you on your worksheet doesn't have hydrogen, which is really weird. But hydrogen has an electronegativity of 2.1. So we can then go through and look and compare. So carbon to hydrogen, I asked you guys to start that last week and then kind of write all of them out. So which one of these has the largest difference in electronegativity? So the most votes was for number 4, oxygen and hydrogen. The difference between those two, oxygen, hydrogen, the difference in electronegativity is 1.4. All right, so the nice thing about this is when you're drawing Lewis structures, you don't have to memorize really anything else when you're looking at polarity of bonds. But you're going to start to see trends where over and over and over again, you're going to see the same atoms bonded together. So the more comfortable you are looking for trends in which bonds are always polar, which bonds are typically not polar, then that will help save you some time looking for polarity in a large molecule. So I asked you guys to write out those 7 bonded groups on this number line. If you have done that, compare it to your neighbor. If you haven't, try to do that really quickly. Determine the difference in electronegativity for all those different bonded groups. Remember, difference of 0, you'd write the bonded group over here, all the way up to the biggest difference on the right. And here's the big chart if you need it, if you don't have your worksheet from last class.
Yeah, that's at the 0.9.
So we're not going to use it's the same thing.
So just to make sure we're on the same page, we're taking these 7 bonded groups, we're figuring out the difference in electronegativity, and then we're writing them on that number line from 0 on the far left to as big as we can on the far right. Go and take another 45 seconds or so to start filling them in on the number line. All right, let's go ahead and start with the ones with the lowest difference in electronegativity. Can I get one bonded pair per volunteer, and then we'll kind of bounce around. So starting from the lowest, Kevin. Oxygen to oxygen. And that value is? Great. Bria. Carbon to carbon. That difference is? Sweet. What's another low value that was in that group? Lauren? What value did you have for that difference? 0.4? So somewhere around here. All right, next and lowest. Another volunteer. Matthew.
Carbon and nitrogen,
What value is that?
0.5.
Great. Next. Love. 0.9. Okay. Next one. Matthew?
Carbon, oxygen,
1.0. Okay. Do we have any more? Ruby? Okay. Does that cover all of them? Anyone find a different value from what we have? Okay, I think all the values that we can look up are pretty standard. It's called the Pauling scale of electronegativity. Does anyone know who Pauling is? Linus Pauling?
I think he was a quantum physicist.
He was a biologist and a quantum physicist. He's the only individual with 2 individual Nobel Prizes in the history of mankind. Crazy dude. Vitamin C was his big thing too. He was really excited about vitamin C. Okay, so we're looking here, and we have these numbers that are pretty small differences in electronegativity. Let's put some up on the far right side as well. Can anyone suggest 2 bonded atoms that would have a very big difference in electronegativity, maybe that you see fairly commonly? Let's do one at a time.
Sodium chloride or sodium fluoride?
Great, let's do sodium chloride. What's the difference between sodium and chloride?
I think it's a little over 2.
What is it? 2.1. Sodium chloride. What would sodium fluoride be? Say again? 3.1. What about cesium fluoride?
3.3.
All right. I just wanted to have a couple values out on the far right side. So now we're going to start to classify things. And there's a rough guideline in that top right corner, but it's a rough guideline. Sometimes the atomic radius is going to play a role as well as a difference in electronegativity between those. So let's start out with ionic. What kinds of bonds do we consider ionic? A big difference in electronegativity or a small difference? So we're going to kind of do this, and we're going to say that anything over on this side of the spectrum, and I really want to emphasize the spectrum nature of this. Maybe in high school you were taught that you have ionic bonds and we have covalent bonds, and they share no commonality whatsoever, or it was very distinct the way that they're taught. I want to argue that they're not distinct. That it's really about how much pull each individual atom has for the electrons in the bond, and that just a slight difference in electronegativity might push it over the line, but it's a gray area. And we're going to say, well, sodium chloride, we definitely say that that's a salt, that's an ionic bond, but it's pretty close to that limit, right? OH is fairly close on the other side. So then what do we call the things that are less than 1.9? So all of these things on the left are covalent, where we say that they share electrons instead of transferring electrons. Once again, it's a spectrum. The ones on the far left share much more equally. The ones towards the middle share less equally. But there's a little bit finer grained detail that I want you to have in the covalent arena. So if electrons are shared very equally or very close to equally, what do we call that kind of a difference in electronegativity? So we have about 0 to 0.4. That was a terrible drawing. That's nonpolar. And then we have polar. So polarity is about having a difference in electronegativity, having electron density closer to one atom than another in a bond. Polar has some characteristics, sometimes similar to ionic. If we're really close to that edge, it depends what else is attached to that atom. And we actually do have examples where an OH can be ionic, and it can split into a separate O- and an H+. That's what we call an acid. So it's part of a functional group that has a certain arrangement of atoms called a carboxylic acid, and an OH can separate. It's not going to be 100% of the time. And that's kind of what this gray area is in the middle here, is that it depends on the situation and what it's surrounded by, that there will be some fraction of the time in which those two bonded atoms actually do become ions and separate from each other. We're going to spend some time with that, a lot of time in second semester, a little bit first semester, talking about strong acids and weak acids and what that means for equilibrium. Okay, so big picture. You need to be able to look at a grouping of atoms, a bonded pair, and decide, is that nonpolar, is it polar, or is it ionic? And then from that, how big of a difference in electronegativity is there, and what does that mean about the polarity of that area in a larger molecule as well? Any questions about what we've drawn up here? All right. So what I want you to be able to do is to take what we just drew, look at a big molecule, and to be able to draw a whole bunch of conclusions. And specifically, first we're going to determine if a bond is polar or not using the electronegativity table. The more you practice with that, the more you'll just know specific bonding groups are polar or nonpolar, and then you don't have to go back to the table. And then we're going to look at a large molecule, identify polar bonds, and then we're going to determine if there's a net dipole around each of those. And so you did have 2 homework problems related to this last night, 2 homework sets that hopefully you were able to work through. And then that's going to allow us to think about relative water solubility. So if a molecule is more polar, we're going to say it's more water soluble, so we're going to be comparing and contrasting different molecules. So I imagine this will be a little bit of review, because the homework forced you to do some of this, is that right? You guys sound very happy about that. The big thing that we want to take away from determining where there are polar bonds in the molecule, or regions of polarity, is first, are there polar bonds? If there's not any polar bonds, don't waste your time doing any of the other stuff. A lot of times students will start calculating angles and looking at different things, and then they'll realize there's no polar bonds and they just wasted their time. So the first thing to do, are there polar bonds? Second thing is, where does that distribution sum up to? So here for carbon dioxide, are the carbon and oxygen bonds polar? First question.
No.
Carbon and oxygen, if we go back to the table that we just drew, it's carbon and oxygen polar. Carbon and oxygen is a difference of 1.0. That's a polar bond. Okay? So then why were we saying no, that it's not polar? There's a second step to that, right? So talk to your neighbor. How do we decide that CO2 is not polar, even though we have 2 polar bonds? Talk to your neighbors, please. All right, we got to a lull. Can I hear a share out from a group that hasn't shared yet? Angel.
Take a stab at it.
Great.
So the oxygens are a little more positive because they're less electronegative. Wait.
You sure about that?
More electronegative.
Okay. They're more electronegative, so what do we expect?
They're more negative than the carbons. so the electron density goes out towards the oxygens.
Absolutely agree. And so that's why we're going to draw this kind of arrow. So we call this a dipole over the top, where the arrow points is the direction that the electron density is being pulled. So that's the more electronegative atom. And then where that electron density is being pulled from, to remind us, we put this little plus mark on the tail, and that tells us that in this case, the right bond, the left side of it is more positive because that carbon has a little bit less electron density than it started with. The other way that you might have seen this drawn is with a delta minus and a delta plus. Does that mean that oxygen has a negative charge and carbon has a positive charge? Okay, so we want to be really careful when we start talking about partial positive and partial negative, and we don't say full positive, full negative. If we were to go in and measure, we could probably measure a difference of about, maybe the oxygen would be about a 0.1 negative charge, a 0.05 negative charge, and the carbon would be a plus of that same thing because the electrons are pulled a little further away. When we do our circle method and calculate the formal charge, well, those electrons actually aren't equally shared. They're a little bit more outside of the range of the carbon.
Just something because it's the same bond on each side and it's symmetric.
Okay, so the first part that Angel was talking about is that there is a polar bond. The electron density is pulled further towards the oxygen than the carbon. Now what you were just suggesting was that that is true, but the same thing happens on both sides. And so that means the electron density is being pulled this way, it's being pulled this way. So there is more electron density to each one of those atoms. But the net dipole, the sum of those two dipoles, cancel out. Joey? So if we were to do this as a physics lesson, you would add up the sum of the vectors. You guys remember doing that in physics class? Okay, so those two dipoles, those two arrows with the plus tails, those are vectors. And so the magnitude of them, how long they are, indicates how big the difference is in electronegativity. So in this particular one here, if I start by drawing A first, so I start at one point in space, that's arrow A, and then where that ended, I start arrow B, and maybe I'll do that a different color, do that light blue. The magnitude of both of them are the same. The directions are exactly opposite, and so the sum of those two vectors is 0. So that means that that has polar bonds. Yes. Is there a non-uniform distribution of polar bonds in that molecule? So then this is a non-polar molecule. Okay, so it's really important we go through those steps first. Are there polar bonds? If so, we draw the dipoles. Does it matter if we know the molecular shape of this compound? Is that important? Why is it, Josh?
Because if you have more bonds than just those two double bonds, especially if you add pairs in, it's going to affect what direction the dipole is going if there is one.
Great, so the big point is we're summing the vectors. If the vectors are pointed in exactly opposite directions, they cancel out. If we had a lone pair on that, are these two vectors going to cancel out? So now the sum of the vectors is not 0. So in order for this to work, we have to have an accurately drawn Lewis structure. We have to determine the steric number. We have to figure out electron pair geometry, molecular shape. And then from that, we can then determine polarity of the molecule. All right, so we have a whole bunch to practice. All right, so let's look at another example here. Let's do these pretty quick, because I imagine you guys can answer these super fast. OH bond. Look it in. Closing out. Overwhelmingly, we're saying that that is a polar bond. Difference in electronegativity, I think we said is 1.4, is that right? Yeah. So that's not only polar, but it's pretty pretty predictably strong polarity on that. So then if we look at the water molecule, can we rationalize the answer that we have based off of the summing of dipoles? Maybe draw it out on your own piece of paper as well. So what do you guys think about this? If I draw water from a different angle, this is what it looks like, right? So we said that water has polar bonds. If we draw it like this, do the vectors cancel out? So what is the step we're missing if this is the conclusion we come to? Can I have a hand raised to describe that, Joey?
The lone pairs.
What about them?
They're not added into this equation. They're going to have some sort of gravitational pull, whatever you want to call it.
So I could argue that if we had the three-dimensional structure of water in front of us in the FED simulation and we turned it a certain way, with the lone pairs, it would look like this.
Yeah, but if you keep rotating that.
Right. So we need to think about the three-dimensional shape. This is your point, and I completely agree with you. That the three-dimensional shape is dictated by the fact that the steric number on the oxygen is 4. That's AX2E2. Electron pair geometry is tetrahedral, and the molecular shape is bent. Okay? So this is a much better way to draw water because then we think about the steric number of 4. We still keep that in mind, but we can kind of show that we know it's bent to some extent. So by drawing it rotated in a way that we can see those dipoles, it's much easier. So then if we were to sum up those two vectors, I'm going to draw one, and then I draw the second. Then the sum of those two vectors is that red arrow I just drew. So vector 1, vector 2, and then you add those up, say where do we start, where do we end? That is the sum of the two vectors. Is it points, maybe I can draw it on the water molecule itself. It'll point from between the two hydrogens towards the oxygen. That's the direction of the net dipole. So you can actually put molecules in an electric field and have a charged, a positive plate on one side, a negative plate on the other side. And once you have it in that setup, you'll actually get the molecules all turning and pointing in one direction, the direction of the dipole.
That's how a microwave heats its food, right? By oscillating the water molecule.
So I think a microwave heats its food by having molecular absorption of microwave electromagnetic radiation. So it's more like what we talked about with quantum, but instead of having individual atoms absorbing energy, it's the molecule itself. So I think that I don't think that that is how microwaves work.
And the length of the vectors is determined by the difference between like O and H electronegativity.
Yes. So if we have, and I haven't really emphasized it yet because we don't have multiple different types of bonds so far with what we've looked at. But when we get into some of the more complicated molecules, if we had a carbon on this side and a hydrogen here, then the magnitude of that vector is going to be shorter if it's a lower difference in electronegativity. So that means the sum would point, instead of straight up, it might be a little bit to the side. Good question. So a lot of times you'll see water drawn like this, where the electron density is shown to be more around the oxygen than the two hydrogens. And that indicates that there's a net dipole that's kind of in this direction that points towards the more electronegative oxygen. Once again, you can also do the deltas. So in this case, delta plus, delta minus, what atoms are going to have delta plus and which atoms are going to have delta minus? Diana? because the electron density is pulled a little bit away from the hydrogens, and it's more pushed towards the oxygen that's pulling it in tighter. Great. All right, now we have a whole bunch of molecules. You need to decide whether they're polar or not. So I think this is on, what question does this start at? Question 5. All right, first molecule is HCl. I want you to determine whether that is a polar molecule, yes or no. Remember, we go through the 2 steps. Does it have any polar bonds? If so, do those sum up to non-zero dipole? You can go ahead and kind of work through all of them if you answer this one really quickly. Raise your hand if you have any questions. Samurai can walk around and help you out. All right, a couple more seconds for HCl, and we'll talk through that one. So let's take one more minute and try to work through as many as you can going through the process. Kind of work through them one at a time pretty quick.
Each individual bond, like C to Cl, C to Cl, C to Cl, C to Cl. What are you trying to add that together for? Right, but if you have a bond, what he was saying is if you have a bond going this way and a bond going this way, they cancel each other out. And a bond going this way and a bond going this way. Yes. So it's not polar. At least that's probably.
What's the size
But it's gonna make them die quicker still. There's more stuff. So what'd you get? I got polar, non-polar, yeah, text from my mom, she was like, yeah, so your cat's outside of the house, we can't get on it. So I have to drive all the way out to get into the house to get my cat, come back inside, which took me like 30 minutes or so. And by the time it's like 30, I'm like, it's a 30-minute drive back to the house.
What about B? What about B? Polar or non-polar?
You see it's really polar. Because it's in a T-shape, right? It's not really uniformly distributed.
Well, it'll be trigonal, planar, and three-dimensional.
But it's still not evenly distributed. Because the two sides
Alright, let's go ahead and talk through some of these.
So it's still not polarity.
So first one, we have an answer clicked in. We have a majority of the class saying that, yes, this is polar. How do we determine that HCl is polar? Matthew?
Molecule.
Because there's only 2 atoms. It's linear. Great.
Atoms and of a total of 8 valence electrons, there's going to be 1 bond and 3 sets of lone pairs on the
Great. And then the big question becomes, is there a polar bond in this molecule or not? So if we look at the difference in electronegativity, what do we find the difference between H and Cl is? 0.9? Okay. And so we definitely draw a dipole. There's only one of them because that polarity draws electrons only towards chlorine. So that is a polar molecule. BF3, go ahead and click in your response for that. I think this one might generate a little more discussion. Just going to give you guys 10 or 15 seconds to click in the answers since you had 5 minutes to work on them. All right. We are split on this one. We are not in agreement. Turn to your neighbor and convince them you're right. We've already discussed this one.
That's why it might be down.
Yeah, I don't know. Between your answer and your
Go ahead and click in if you've changed your answer.
because one doesn't hold yes.
A couple more seconds.
But I thought boron and beryllium did.
I love clickers. So cool. See the shift in numbers. I know people change their mind. A significant number of people change their mind. Can you describe why you changed your mind? Anyone like to volunteer? What did you learn, and why did you change your mind? Those people just want to stay anonymous. Would anyone like to tell me why someone might change their mind, Mohib?
Okay. Well, it's like the way Sam explained it to me, which really makes sense, is that it has, if you draw it to the Lewis structure, there's no lone pairs, right?
There's no lone pairs?
That's
You mean on the central atom, possibly?
That's what I meant. Yeah.
Great.
We're
on the same page.
Atom, there's no lone pairs, so you're gonna have like a trigonal planar geometry with, and so you see that they're all the fluorines are spread out equal.
Okay, and pause.
Okay.
Before we even get that far, what was the first question that we asked ourselves? Are there any polar bonds in this molecule? If not, then we don't need to draw the structure to determine that they all cancel each other out, right? So are there polar bonds in this molecule?
Yeah.
They're actually really polar, right? Difference is, what, 2.0 I think we found?
Yeah.
Difference in electroactivity. So that means that they might even be considered ionic. Remember, it's a gray area. It's not a hard cutoff. Fluorine is really small, and so they're actually going to be closer together to that boron, and so they are more polar than they are ionic in character. So then we drew out the structure, and then we say we're going to add the dipoles to each individual bond. Which way does the dipole pull? Towards fluorine or towards boron? And then if we add up all three of those, we're going to go out here in space and draw maybe 1, 2, 3. Draw it down. Maybe I did that wrong.
Whatever.
We add together all three of these dipoles. There's the first one, there's the second one, and there's the third one.
0.
So they all add up to 0. So is that a polar molecule or not?
No.
No. Does it have polar bonds? Yes. So it doesn't change the fact that it has polar bonds, just like CO2. Okay? So I agree with Sam's teaching of Mohib. Thank you. All right. What about NH3? Go ahead and click in your response for that. Now, polar or non-polar is referred to how partial ones that are not being shared. It's the extreme of polar. It's called ionic. All right, closing out. We have a very strong agreement here. Can I get a new voice to describe how you concluded polar, non-polar for NH3? Aaron? So they being the bonded atoms N and H? Great. So
And then I determined the structure of them because we know that drawing out the structure, nitrogen is not going to pair on it. It's trigonal pyramidal, which means that one of the vectors
great. And so one of the big things I wanted to emphasize with these two structures is that both of them, if we look at it, they both have polar bonds. We're going to say that they're both non-polar because they all cancel each other out, right? But there's a big difference once we draw the molecular shape and we show that these are trigonal pyramidal. So those differences in electronegativity, those dipoles, are not going to cancel each other out, but they did in BH3. So knowing where those atoms are in space becomes very important. We need to know the electron pair geometry, but it's a molecular shape that ends up influencing the answer of is it polar or not. All right, so then let's go ahead and do carbon tetrachloride. This stuff's nasty.
Probably still not as bad as carbon tetrachloride.
That's not very common. Carbon tetrafluoride is pretty common in organic labs.
Yeah, but
nasty.
I still wouldn't want to deal anything with any fluorine complex. Like any polar or any covalent fluorine complex. It has to be always.
Fair enough. All right, we got almost everyone in. Let's go through the two questions relatively quickly now. First question, are there any polar bonds in this molecule? Yes, what's the difference between carbon and chlorine? 0.5? Okay, so we have polar bonds. Then we draw out the molecule. What's the molecular shape of this molecule? Tetrahedral. So we know that all four of those domains are spaced as far apart as they can from each other, equally in space, which means that if we could four-dimensionally, three-dimensionally really draw these out, we would have all of them cancel each other out. And that's nonpolar. So it becomes a bit more difficult once we get past trigonal pyramidal, because we're trying to draw where do all these end up having a dipole. If we were to go back and draw NH3's dipole, it does go up from between all the hydrogens through the nitrogen towards a lone pair. All right, let's go ahead and do the last one. I'm going to reopen this. So go ahead and do the last molecule here.
I'm noticing a pattern. If there's a lone pair, then it's generally polar.
If there are polar bonds. Absolutely.
What I see.
Couple more seconds. All right, if we go ahead and ask the first question, are there any polar bonds in this molecule? Do we consider CH to be polar? It's right on the border, right? 0.4, 0.5, it's 0.4 difference. One of the trends I want you guys to internalize is if it's same, whatever those two atoms are, it's nonpolar, because there's no difference in electronegativity. And then carbon-hydrogen is one of those ones that as chemists we typically say is nonpolar across the board. I think your homework, I saw a problem where it actually said, is there a difference in electronegativity? The answer is yes, there is a difference, but it falls in that category of nonpolar. So we have a whole bunch of nonpolar CH bonds and then one polar CCl. So if we only have one polar bond, is there any way that that's going to cancel out with another dipole? Kind of goes back to this, right? There's nothing else to cancel out that dipole because there are no other polar bonds around either of these atoms. Same thing's true here. So we have one dipole. That means that the dipole of that entire molecule is dictated by the one polar bond. All right. So there's a summary of that in the next couple slides. I'm not going to spend much time on. But you can actually measure that difference in electronegativity in Debye units. And so you can actually calculate how strong the difference is in electronegativity in the individual atoms and what the sum of that vector is. So you can see down here where there's a lot of vectors that cancel each other out and how that changes as you get less and less of that net dipole being canceled out. You can actually measure a bigger and bigger difference, and you can do that by having the two plates, a positive and a negative plate, and seeing how much of an interaction there is between the molecule and those two plates. So then let's look at these two. Out of these two molecules, ethanol is more water soluble than ethane. I want you to talk to your neighbor and try to figure out how to describe why that is. Why is ethanol more water soluble than ethane? It's question 6 in the back of your worksheet. All right. Lull in conversation. Can I hear from a new voice? What ideas do you have? Gail.
Is it because ethanol is polar?
Okay, so ethanol is polar. What about ethane?
Non-polar.
Nonpolar. Why do you say that ethanol is polar? What did you notice about it that stuck out?
Well, because you have the oxygen, it's going to have lone pairs, and it's not going to be symmetrical.
Great, so if we focus in on that carbon right there, it has two hydrogens, one carbon, CH3, I'm not going to draw that out right now, and then it has an O and an H. What I was talking about before with pattern recognition, carbon-oxygen, always polar. Oxygen-hydrogen, always polar, a bit more polar. So we have two polar atoms, or two polar bonds, sorry, and we know that there's two lone pairs there. We know that's going to be bent. That means that there's going to be a net dipole there. Whenever we're looking at a molecule and we see an OH, that's the first thing we want to think about. What about over here on the left? Are there any polar bonds?
Yes.
Polar?
No.
There's difference in electronegativity between carbon and hydrogen, but they're not strong enough to be considered polar. So this is a non-polar molecule. That's a polar molecule. So the question is, why does that make it more water soluble?
Because water is polar.
Good. Nice and loud?
Because water is polar.
Water is polar. So there's this really basic saying, like dissolves like. That holds pretty true in chemistry. and it has to do with intermolecular forces that we'll be talking about later, I think at the beginning of the second semester. It's about how if you have two molecules next to each other, that net dipole from one molecule will be attracted to another one with a net dipole. If it doesn't have a net dipole, it's going to be very little interaction with something that does have a dipole. So we know that water has a dipole. That means that things with a dipole that are polar are going to be more likely to dissolve within that solvent. So then let's take a look at these two. Which one of these two compounds do you think is going to be more water soluble? And I should have put C, being that they are both probably equally soluble. So go ahead and talk to your neighbor, try to decide which one of these you think is more water soluble. With how many hydrogens? How many bonds does carbon have? What's that? So I'm expecting you guys to be able to use line structures. What is where my finger is right here at the far left of that acetone molecule? Carbon, how many hydrogens?
Acetic acid.
I don't know what I said.
You said acetone.
Oh, it's not acetone, right? It's acetic acid. So there's a carbon there. Carbon always has 4 bonds. It's only showing 1 bond to another carbon. So there's a CH3 here. Over here in this molecule, this carbon is sticking up towards us. It means that there's another carbon at the top. There's 3 hydrogens around that. Are there any hydrogens on this carbon at the base of that? There's 1, 2, 3 bonds shown. Carbon has to have 4 bonds. So there's 1 hydrogen there. We should be able to go around a molecule like that, identify exactly how many hydrogens there are, how many carbons there are. That is something that I will test you on next Monday. So if you're not comfortable with that, make use of office hours or practice with your peers. Okay, so if we look at these, which one do you think is more water soluble? We have a split distribution. Anyone like to argue their case? So some people are saying they have the same, other people are saying that this is the more water soluble. Let's hear from new voices we've heard from a couple times. Anyone like to argue which one and why? Which are the answers? Eric?
They're the same. They have the same oxygen and hydroxide bonds going on, and the rest of it is not polar.
So you're identifying this functional group called carboxylic acid. Both of them have that. So then why is acetic acid much more water soluble? Much, much, much more water soluble. If you think about the polarity of this overall molecule, think about the sum of the dipoles compared to the entire molecule. Versus on the right side, ibuprofen has dipole, the same dipole, but then it has to carry along all this nonpolar stuff and try to bring that into water. All that stuff that doesn't want to dissolve. Think about it as oil. Trying to pull all that oil into water, but it's much more difficult. And so there's actually a new formulation of Advil that takes this H off and puts an Na plus on there instead. So you end up with a salt of Advil that makes it much more water soluble. So what I want you guys thinking about is it's not just the number, but it's the ratio of polar bonds to nonpolar bonds and how polar those bonds are. So what you should do for practice before our next class is to look at the molecule that we were looking at before, go around to each individual atom, determine is there a net dipole or not. So go through those steps. Are there polar bonds? If there are polar bonds, what is the molecular shape and how does that determine what the net dipole is? All right, we'll see you guys on Wednesday. We'll be talking about hybridization.
Oh.